Okay, so this week we have three problems in the theme part, but then we'll also start with two easier problems. So warm up. So let's just quickly go through the first two. First one, we have excuse me, we have a bunch of bees, and basically, if a bee, if a beehive is within a certain distance d of another hive, then they will be bad. Otherwise, they'll be good. So basically, all you have to do is for each beehive, check if there are any other beehive that is close to it. And if so, then it's bad. Um, Now, we don't have to do anything smart here because um, the number of beehives is the most n. So even if for each beehive we check all the other beehives, that's n squared. 100 squared is nothing. So all we have to do really is to make sure that we know how to check if two beehives are close. And we use the standard Euclidean formula, right? The difference in x squared plus difference in y squared, square root, but we don't like to stick square root because that introduces more rounding errors. So we'll compare it with the distance square without taking the square root. So this is a standard trick that we've done a few times now. So I won't say too much more. I'll just jump straight into the code. So here's my solution. I have square distance computation between 2 points. So basically, it's the Euclidean distance without taking the square root. And then for each case, so because this problem, you need to deal with a number of cases. So um, you read the D and the N, and if they're both zeros and there's no more case, otherwise you do something. What do? You read, actually, I guess I misread the problem. I thought it was 1,000 points because I see the 1,000 there, but actually it doesn't even matter because even 1,000 points is good. N squared is good enough. So I read it in the X and Y coordinates. I remember how many sour points there are. So for each point, I check every other point. So don't check if I is equal to J. And then I ask if the distance is too close, then I add sour plus plus. But then I remember to break because once I found something that works, that makes it sour, I don't have to check for any other ones. And then possibly ruin my counts if somebody's close to a certain beehive, if there's three different ones close to a certain beehive, I only want to count that once, not three times. And at the end, I just print it out. And if I know how many are sour, then the rest of them and minus sour is sweet. Okay, there's not too much more for me to say, so I'll just move on to the next one. Okay, the next one is also another warm-up problem. You have a recent election and you want to know if there's a clear winner. So there are a bunch of people's names. Star, star, star is the end of inputs, and it's not a real candidate. A naming consists of multiple words separated by spaces. Words can contain letters or hyphens, but no other punctuation characters. So you have to be sure to read both of these as one name, right? So just be careful here. Use get line, for example. There'll be at least 2 votes, up to 100,000 ones. If a candidate obtains simple or absolute majority of all vote cast, that is more than any other candidate, I'll put the name of this candidate. Otherwise, I'll put runoff. Don't forget the exclamation mark. So basically what we have to do is we have to keep track of how many times each name appears. Then remember, right, and try to figure out what is the maximum number of votes anybody gets and see who has this number of votes and if there are more than one. And the usual way to keep track of the number of times you see something would be a map. So map of this name to an integer. So the code, it's just here. So I have a map that keeps track of the frequency of the names. Toto is the Toto. Actually, I don't think I'm using Toto anymore. I misread the problem. I solved it for a different problem. So I need a Toto, but actually you don't need Toto. So while you read in the name using getLine, so this is going to return true if it was successful. Otherwise, it'll return false if it's, for example, EOF. This will always return true for this problem. What I really want is not to write this multiple times, so that's why I put in the while loop. But the most important thing here is that the name is not star, 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 because when it's star, 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 you're done. What do you do then? Well, you just put it in the map. So put it in the map and increment the corresponding frequency. In the meantime, I also keep track of maximum the votes that anybody got. And I have to do plus plus. So I update this before I update the maximum vote. If you don't like writing all these in one line, you can write in multiple lines. Update the frequency first, then update the maximum vote. So now I know not only the frequency of everybody's votes, but also what is the maximum number of vote that anybody got. So then I have this thing called winner that keeps track of who won. I go through the map. Remember in the map, the first entry is the name. Second entry is the frequency. So if the frequency is equal to the maximum vote, that's a potential winner. But I might have already found a winner before if I have multiple winners. So if the winner is the empty string, which is the default value, that means I haven't found a winner before. Then I set the winner to be whatever name I found. Otherwise, I have already found a winner and I found another one. I print one off. And then when I print one off, I just quit. And then if I'm here, that means that I have only found one winner. So I'll just print the winner's name. Okay, so that's the second warm-up problem. Now let's get to something a bit more interesting and involved. All right, tight words. Okay, so tight word says you have an alphabet, 0 up to 9, 0 up to K, where K can be up to 9. So basically a certain number of digits you can use. We say that a word of length n over this alphabet is tight if any two neighbor digits in the word do not differ by more than 1. So for example, K equals to 2, you can only use digits 0, 1, and 2. The tight words of length 2 are these ones. But 0, 2, for example, is not. And neither is 2, 0. Okay, and then the percentage is 7 out of 9. So input is a sequence of lines. Each lines contain 2 integers at K and N. N is at most 100, K is at most 9. And then you're supposed to output the percentage. Okay, so percentage is basically, what's the percentage? Percentage, it's equals to the total number of tight words divided by the total number of the words of any kind. Now, if you have K, whatever that is, you're allowed to do 0, 1, 2, up to K. So that means that K plus 1 choices, okay, this is K plus 1 choices. And each position, you can choose any one of them, and the n positions. So the total number of words, it's K plus 1, raised to the power n. That's the easy part, I guess. The part that is not so easy, this number of tight words. All right, so what do we do? We have n positions, dot, 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 n of them. And for each position, you have to choose sum, whether you can use 0, 1, 2 up to k. Well, the first position you can do whatever you want. So k choices, but then later on, maybe at some position, what can you choose here? Well, you cannot just choose anything. You can choose something based on what's chosen before, right? If this is chosen as a 5, then the next one can only be 4, 5, or 6. You cannot choose 3 because that's too far apart. But if this is, 2, then you can choose 1, 2, and 3. So what you can choose at any particular spot depends on what the previous digit is. All right. So somehow you have to know what is the previous digit. And you want to know how many tight words are there of a certain length. And, right? So this is a question that you really want to know. But in order for me, so what I'm going to do is I'm going to look at if I have a bunch of choices, right? I have n choices. I need to look at, let's say, the last choice or the first choice, doesn't matter. Pick one. Pick either the first or last choice, you pick the last choice. So if I want to know what can I put here, can I put a 0? Can I put a 1? Can I put a 2? Can I put a 3? What if I want to put 4? Right? If I want to put a 4, what can I attach it to? If I put a 4, I can attach it to a tight word of length n minus 1, but it can only do that if the tight word of length n minus 1 ending at 2, sorry, 3, 4, or 5. So what do I want to say? If I can recursively ask how many tight words there are of length n minus 1, so that's the recursive part from n to n minus 1, but somehow we need this extra parameter, 3, 4, and 5, what it ends at. But wait, I'm calculating this, the length n ending at 4. So even though originally we are not asked how many tight words are there of a certain length with a certain ending, we might actually want to change the question ending at digit, whatever, D. So we're going to change the question a little bit and ask this question, because if we know how to answer this, then we just answer this question for n0 and 1, try all the different n digits and add up all the answers, and that's our answer. And by changing my question, it allows my recursion to be easier because now I can have control of what is the digit that I ended with. Okay, so this is a little trick sometimes that I actually make the problem a little bit harder by adding more parameters so that I can easily do the recursion of the same type, because when I do recursion, I have to do it the same time. So why do I do recursion? Because now I can solve this problem. Okay. So if f n d is exactly this, the number of tight words there are of certain length that ends at a certain time, at a certain what do they call it? And at a certain digit, then I can compute a few things. So recursion. So what is the easiest case? Okay, so if I have exactly length 1 and ending at that digit, well, then just is one single string containing that string. Okay. So if somebody say, what is the number of tight words that's length 1 and ends with the digit 5? Well, then it's just the string 5. That's the only string possible. So the answer is exactly 1. Okay, so for any d, f of 1, d is exactly 1. Now, what about in general? Well, we can attach it to any one of these. So we can attach it to a string of a smaller length, provided the digit that it ended with, it's not more than 1 apart. So it can be any one of these, but you have to be a little bit careful that some of these might be invalid. So for example, if you're computing f of 3, 1, then you recursively would say this is f of 2, 0, sorry, try 0. F of 2, 0 plus the f of 2 minus 1 plus f of 2, 0 plus f of 2, 1. Well, you can either say that if the d is out of bound, then it's automatically 0, or you can just not include a sum. So you can say f of anything, d, it's 0 if d, it's, excuse me, it's less than 0 or greater than k. So that's another way you can do this. Okay, or if you want, instead of saying how many, we can say proportion. So that's what you're actually computing. Then basically you have k plus 1 n times. So we just distribute this k plus 1 at each step. And that's the other way of doing it. And this actually is better. Why? Because if I actually compute the total, like k plus 1 raised to n, or this, it will actually overflow for 100 digits long. So it's better that we compute a proportion everywhere. So that's basically the recursion. Okay. And now this is classic dynamic programming. So we're going to go and look at how we implement the code. And which I don't know if the code that I have is exactly what I wrote. It doesn't really matter. So this f, okay, so instead of d, I use k here, but then I use max digits, which is k plus, where's max digit is k. So if n is, so first of all, I have a table. So I'm using a dynamic programming table. I know that it's at most 0 to 100 for n, and k is 0 to 9. So I need 101 entries in one dimension and 10 entries in the other one. I read in the k and n. I set the max digit. I set all of them to be -1 in the table. Okay, so it's -1 because I have never computed it. Okay, so that's the idea. I make sure that at the beginning nothing is computed. Then I call f of n for each ending digit and add up the answer, and then at the end print the answer. So how do I do this? First, I check if the table entry has been computed. So if it's not -1, if it's bigger than or equal to 0, that means I already computed it. So I just return it. So this is the key point of dynamic programming, in that this recursion, if you don't save the result that you have already computed, this can take forever to run because you end up doing the same work over and over and over again. And we don't want that. So this is a trick. The first thing is to check, have I seen this before? If I have, just return. Then the base case, if n is 1, then the percentage is 100% divided by the k plus 1 that we talked about. Otherwise, it's the sum of three things, d minus 1, d, and d plus 1, all with n minus 1 in the first component. So here's the code. So I set that to be 0, and I sum up k minus 1 to k plus 1, and then add that up. The max 0 here basically means if it's negative, don't use it, start from 0 instead. And here, if it goes out of bound the other way, stop it at the outer bound. So don't go beyond that. Okay, but basically this is a loop that adds up to 3 sums, possibly less, but add 3 things together at most. Okay, so that's tight words. So, I guess what is the story here? The story is to recognize that this is dynamic programming, but you start with trying to figure out how to count how many words there are. And then, you have n positions, so you have to for each position, you have to choose a digit. You have a bunch of choices. You have n choices in sequence. So the standard thing to try is to figure out what if you think about just the first choice or just the last choice. Can you do recursion on that? You can also think about how, instead the way that we do it, look at the last choice. You can actually do the same thing, thinking about the first choice. So instead of saying proportion of tight words that are certain lengths ending at a certain digit, you can say starting at a certain digit. And then you would say, okay, if I want to know what are all the words of length end that starts at digit D, well, it's the order. Basically, you have to attach it to words of digit n minus 1 digits that starts at digit D plus minus 1, D, or D plus 1, and so on. And you basically run the recursion the same way. Okay, so that's that one. This definitely is not the easiest problem, but I do think that is a good practice. Okay, short sell. Again, I assume that you've read the problem, so I'm not going to say too much more. Basically, you have a bunch of prices, 5 of them in this case. So the first number is how many prices you have. And then at each day, you can decide to sell something that you don't have by borrowing it, and then buy it back later. So the idea is that, let's say you sell it on this day, so you get $1,000 per share. You sell 100 shares, so 100 coins or whatever. So you actually end up with you're actually making $100,000, and then later on when you buy it back, I don't know, let's say here you only pay $10,000 to buy it back, so you make the profit. But the problem is that every day you have to pay when you do this to sell first. You have to borrow somebody's shares to sell, so you have to pay some interest every day that you borrow from the first day. Okay, so I have a bunch of number: price 0, price 1, price 2, price n minus 1. These are the prices. And let's just forget about this factor of 100. I'll just pretend that all the numbers have been multiplied by 100 because I'm always buying and selling 100 coins anyway. So if they give you the price is 100, then I really just want price to be 100,000. I'm sorry, 10,000. Okay, so you want to know when do you want to sell, and then when do you want to buy eventually. You want to sell high, and you want to buy low. The tricky part is if you sell something at the quite early, you're going to accumulate this penalty for the interest. So holding onto it longer and longer can get you worse and worse. So what we're going to do is we're going to try all possible time to buy. Okay, once you buy, there's only one transaction. You just sell once and you buy once. Okay, so once you decide to buy, you never do anything again. And you want to make the maximum profit. Okay, so that's our goal. So what we're going to do, we're going to try all possible place to buy on day I, let's say. So if we want to buy, we must have sold at some point previous. Which day do I want to sell? I want to sell it at the best possible day. So I want to know what is the max profit. No, actually shouldn't use the word. It's the max price from day 0 to I minus 1. I could sell. I could sell that, right? So now it could be like 10, 10,000, and then could be like 9,000, and then maybe it could be like, I don't know, 2,000. And you just say, oh, the max is this one. But maybe it's not so clear because it depends on how much interest you have to pay, right? So if the interest that you have to pay, it's more than 1,000, then holding on to this for one more day, maybe it's actually less than taking this 9,000 later. Okay. Or to make things a little bit even more dramatic, if this is 2,000, this is 9,000, then even though the 10,000 is bigger than the 9,000, if you have to pay the interest to borrow this 1,000 a day, then you take this for one day. Actually, you count the first day too. So by the time you get here, it's 3 days of interest. This 10,000 that you sell is only worth 7,000 by now. And so it's better just to take the 9,000, which is actually worth 8,000 because you have to pay interest too, but it's still better. So basically what you want to do is you want to keep updating what is the max price that you can sell something at with the interest. Whatever it is, so you know that on this day, you can get a certain amount from selling. So I don't know, in this case, let's say the best thing you can get is 7,000. So why 7,000? Because 9,000 is best, but when you get to the second day, you have already paid 2 days of interest. Okay. And then this, if it's like, I don't know, 2,000, you know that you can sell something and keep 7,000, pay $2,000 back, and you make a profit of plus 5,000. Okay. And now you also want to ask, okay, what about the next day? When you get to the next day, well, the best cost, the best price you can get, it's either whatever it used to be minus another 1 day of interest, which is 6,000, or you take whatever this price is and use it from scratch and then decide to sell it. So in this case, it's 2,000 minus 1,000, which is less than this. But if this is like 12,000, then this will be bigger than the 6,000. So basically what you do is you keep updating this as you sweep. So you sweep from left to right. For each day, you keep track of how much money you could have been holding by selling something in the days before. And if that is bigger than what you can buy back for today, you buy. That's one possibility. And then you just move on next day and next day and next day. And so again, this is dynamic programming in the sense that we're taking the result of this question, okay, this question from a previous day and building onto this every day and updating this. The way that I wrote this, because it's a simple sweep, one parameter, I did not use recursion, although if you really want, you can use recursion. So what's the recursion? So you can say if this is f I is this thing, then f of I, the recursion would be f of I minus 1 minus the interest, because you have another, whatever you had before, one more day of interest. And then pick the maximum of this and price of I minus 1 minus the interest, because you have to borrow that on day one. Pick whichever one. And then there's the f of 0 is 0, let's say. Okay. So that's one way to do this recursively if you wish. But if you do this recursively, then you have to make sure that you, again, do a table that stores results that you have already gotten, because otherwise you'll end up doing the same problem over and over again and blow up on the complexity. So here's my code. I have what I call, okay, so I read in this prices and I multiply everything by 100 right away. The best profit, that's my F so far. This is to keep track of the best amount that we can sell things for. So, sorry, this is the best profit is what I'm trying to keep track of in the answer. Best sold is the F that I was computing, the most amount of money I could be holding right now based on what I've sold before. So every day that I have, I lose K more dollars for paying interest. Then I try to buy it back. Now I try to buy it back. I don't even care if buying it back makes me profit. So if this is negative, then because I set the best profit to be 0, I would not have updated my max. And then the best sold is just whatever amount I can get today based on what I've sold before or sold it today. And then just update that and that's it. So the code itself is quite simple, but it does take a little bit of work to think about what's going on. Okay, the last problem, presidential election. Okay, this one is pretty complicated. And I'm not going to show you the full code. Well, maybe I'll show you the full code. Basically, you have these districts or states where each state has hold a certain number of votes, DI, and then there are two parties. There's some parties that are some people that always going to vote for C, some people that are always going to vote for F, and then there's some undecided voters. And if you can win that state, then you get D votes. Then you want to have it. You want to have more than the other party. Okay, so again, you need to read this carefully because I don't want to tell you things that are already in the statement. But basically, you have to decide there are a bunch of states. Each of the states have a number of delegates, number of people that votes for each party, and then undecided. So some states will always, no matter what you do, C will win, the one that you want, I think. I don't remember which one is which, doesn't really matter. And some states F will always win. So those you just can't do anything about. So how do you know that C will always win if C is greater than F plus U? Even if all the other voters turn to vote for the other side, you will still win. And then the ones that you will always lose, it's in this case, even if you can convince everybody to vote for you, you still lose. So now, if you're not one of these two cases, so this C wins no matter what you do, this F wins no matter what you do. But there are other cases where it's not one of those, and you might be able to convince some people to vote for you. Okay, so if you want to convince a certain number of people, let's call it M, to vote for you, then the other people that you don't convince, it's going to end up voting for the other one, right? So you manage to convince M people to vote for you. The rest will vote for U minus M. You want this to be true because you want your total vote to be more than the other guys. So what is M? We can solve for this. 2M is equals to F minus F plus U minus C, or F is equals to F plus U minus C divided by 2. So M is the number of people you need to convince in this state to win the district, assuming that you're not in one of these two categories. Okay. So now what? Right, you can compute this. So for that state, you can figure out how many people you need to convince. Maybe a small number, maybe a big number, who knows? But there'll be a number. Okay, now there's going to be, how do you compute this? Right, you want to be strictly bigger. So whenever you divide by 2, right, you have the problem that you might divide something exactly right, or maybe it's not even and you have a 0.5 that you have to deal with. So let's think about the two cases. If you have even, so let's make it simple. Make it, let's say 10. Pretend it's 10 just for illustration purpose. Then 10 divided by 2 becomes 5. If it's odd, let's say 11, it also becomes 5 if you do integer division. But in either case, you don't want 5 because you want it to be strictly bigger than this thing over 2. So if you do plus 1, it becomes 6. And it will work no matter whether you even or odd. So for each state, assuming that you are not in one of the situation, the number of people that you have to convince, it's F plus U minus C slash 2 plus 1. Okay? So each state has these are the number of people you have to convince. All right. Now what do we do? Again, we have a bunch of states. You have, for each state, you have a D, you have a C, and you have a U. And we can also have the M. M is the number that we compute. Now, the states that you're going to win, so you have a bunch of states that you're going to win for sure. You just got to count how many delegates you have. That's easy. Okay, those you already have in the bag. No matter what you do, you can just set these to 0. You don't have to do anything. Okay, now the ones that you're not going to win, you can't do anything. So you're going to lose anyway. So you can just ignore. You can't do anything anyway. The rest, you can try to influence with M, whatever M you computed from the formula before, that's how many people you have to influence. And you might influence, I don't know, 10 people and you will gain you 3 delegates. Or maybe this state, you know, have to influence 4 people and give you 5 delegates, and so on. At the end of the day, you know the total number of delegates you have and how many delegates do you need? You need at least this much. So just the same formula as before, divide by 2 plus 1. You need that many. You already got a certain number, so you can remove that from the total. And whatever you need, you have to grab it from these that you can influence. And you have to decide which one to influence to get you at least this much. And now, this is a typical what we call knapsack problem. So you have a target total, which is at least this much, but it could be more. It's okay to win more. And you can use a bunch of items, each 0 or more times, 0 one time. Either you use that item or not. And the item has a value of D, okay, because that gives you D delegates, and a cost of M. And you want to get a bunch of items. Each item use 0 one time, so that the total value is at least this much. And you want to minimize the cost. And this is a typical what we call knapsack problem. So in the knapsack problem, you have a big knapsack. So this is a knapsack of some capacity, capital C. And then you have a bunch of items which has a certain weight, W, and certain cost, little ci. And you want to pick a bunch of items so that the weight adds up to the sum of the weights is less than or equal to a certain capacity, and you want to minimize the sum of the cost that you chose. Like that. But the way that you usually solve this is to not ask for this question, but ask for, can I choose a bunch of items so that it's exactly a certain capacity, and then you try different capacity that is under this. So what are we going to do? We don't have capacity here. We have the total delegates. Our weights are the DI. The cost is this M that we compute how many people you have to influence to win that district. We want the sum of DI to be a certain little d, minimizing the cost. And we're going to try D that are at least the total number of delegates divided by 2 plus 1. And we're just going to try them all. And this, we will write F of D, comma, N, where N is the number of items. Okay, so if you have N items or N states that matter, right? We only worry about the ones that you can use to influence. It's the min cost to achieve total of D using items 0, 1 up to n minus 1. Okay, this is a standard knapsack problem, two-dimensional. And what you do is you say, okay, do you use the last item or do you not use the last item? Those are the two choices in knapsack. So the recurrence goes like this. So if it's base case, if you're not allowed to use any items, then the cost of making the sum 0 is 0. Okay, so if you're not allowed to use any items, the cost of doing nothing, basically forming a zero sum is 0. You don't have to do anything. If it's any other one, if it's any other D, but you're not allowed to use any items, then we say it's infinity. So it's impossible, basically. Okay, so that's the base case when n is 0. So what about the general case? For any other n, if n is greater than 0, then I either use the last one or not. It's the minimum of two possible things. I can decide not to use that item, so I still have to form the same sum, but I use one fewer item. Or I use that item, so I use mi, so not mn minus 1. So I use that item, so the cost, I have to add it to the cost. But now, because I've used that item, I will need to make up something. I can make up a total that's less by that much. Of course, this has to be non-negative, right? If you try to make 4 delegates and the DI is 10, then you can't use that item. Okay, so you have to be a little bit careful if it's done this way. But that's basically it. Okay, so I know that I'm going a little bit fast because if you didn't know knapsack, maybe this is a little bit out of reach for you, but at least you've seen this problem and hopefully you can have a look at it a little bit. And then if you've seen knapsack before, this is how we transform the problem into a knapsack problem. So my code, I have the knapsack part, and then I have the part that I do to form the knapsack. So I read in everything, the total number of delegates. This is just summing up all the D's. Number of votes for sure. For C, actually, this is number of delegates for C for sure. So this is the total number. This is threshold. So I did it a little bit differently, computing the M. But anyway, it's just the same formula, it's equivalent. So if you already won for sure, there's nothing to do, just add it to the total delegates. Otherwise, sorry, the delegates that vote for you. Otherwise, figure out how many more voters you need. So that's the M that we talked about. Check if you can influence it at all. If so, now you have another new item in the knapsack for weight D and cost C. This thing needs C. And then how many delegates you really need, at least. It's the total divided by 2 plus 1, total delegates divided by 2 plus 1, but then minus the number of delegates you already got. Now, it's possible that you already have enough, and you actually don't need to do anything. So I make sure that if this is somehow negative because you already have too much, then I just say I need 0. Knapsack here, it has set this memorization table to -1 to say it's not computed. And then I just try all possible number of delegates, total number of delegates to get from what I need all the way to maximum. And for each one, I call f of d with the number of items and just keep track of the minimum. And then this is my standard knapsack recursion. I asked if I've already seen it before. So if it's not -1, I've seen it before, I return the answer. I just use a reference here so I don't have to keep typing membo dk all the time. This answer is just a reference to this thing. If k is equal to 0, then the base case, if I'm trying to form the sum 0, then it's okay. Otherwise, it's infinity. I have to tell you what infinity is later. Otherwise, it's possible two things. Either don't use item k at all, or k -1 at all, or use it if possible, and you use it only if it is possible. If the weight of that it's less than or equal to the weight that you're trying to form, and then you recursively call this, which is what I wrote. And then because this can return infinity, if this is not possible, so I just do a min infinity to make sure that it doesn't go too big. Okay, so that's whatever I said sounds a little bit funny because how can an infinity get too big? Because my infinity, there is no such thing as infinity. So I put infinity being 1 billion plus 2, actually 1 billion plus 2, because they said that the total number of registered voters at most 10 to the 9. So no possible answers can be more than 1 billion. So I just make +1 is good enough, but +2 just to be safe. So infinity 1 billion plus 2 is just as good as any infinity. And I like to have it as 1 billion, a little bit over 1 billion, because in case I do this part, in case this part comes back infinity, and this part is about 1 billion because I can have up to 1 billion voters, these two numbers added together can be at most 2 billion. And 2 billion still fits inside a normal 32-bit integer. Okay, so I think this infinity is chosen a bit carefully here. If you don't like this, you can choose either infinity and maybe use 64-bit integers, or maybe find some other way to mark that it's not possible. I don't know, maybe -2 or something like that. But anyway, if you can find an infinity that works, sometimes makes the code a lot simpler. So you don't have to check for, is it some other special number to indicate it's not possible. Okay, so this one is definitely the hardest one out of the 5. It's the last problem, and we want to have something that challenge people a little bit. You're more familiar with dynamic programming. So I'll stop here today, and I'll pose another problem set next week.